It's one of those things you always think you shouldn't have to make. Cool Hard Logic keeps saying you shouldn't have to answer this. That is an Earth fact sheet from NASA themselves. Behold, nasa.gov. You're entitled to decide this means it is utter bollocks. But, you know, if you want to talk about NASA's globe Earth model, you can get data such as how long it takes to go round, how far from the sun it gets, how close to the sun it gets, not necessarily in that order, how much mass it has, how big it is, what the radius is at the equator and distance from centre to the pole, mean radius, core radius, yada yada yada. All of this stuff from NASA themselves. So if you want to talk about the Earth, the Moon, and Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and the Sun, as NASA described them, get the information, this stuff, about the celestial body, that thing, from NASA themselves, that place. And if you do that, you can produce actual models. Now you may have seen a lot of you've probably seen posters of the solar system, and they've got the Sun looking like this, then you've got Venus, Mercury, Venus, Earth, Mars, Jupiter, Saturn, kind of here. And it's easy enough to do that. Where have we got? That one. Picture of the Earth. If I just, on an image search, just type in solar system, image search, and there you go. Dozens of examples of main masses of the solar system, all stuck together. This one nicely includes the asteroid belt there. Here you've got just some planets, all drawn the same size. Here you've got the size of the Sun and the size of the inner planets and the size of the outer planets, presumably to scale. But they're all nicely close together so that you can see them. They've left Pluto off. Terribly rude to people who like Pluto. Here's an older image that does include Pluto. And they've got orbital paths, and I don't think those are to scale. I really don't. I think they've gone arbitrary on the scale there. But again, you see all of these things. There's a nice little diagram with them all laid out at different angles, and tend to be drawn in a straight line so that you can see. Here's one with numbers so you can compare them. None of those are to scale. This is certainly not to scale. This is not meant to be what the solar system actually looks like. That is neither. But what you can do with all of these here fact sheets, Sun, Mercury, Venus, Earth, Mars, helps from actually looking over here, doesn't it? They include pictures? They do! How pretty. The Sun, Mercury, scroll up, Venus, nice that we have a coloured photograph, Earth, very pretty, the Moon, yes, we all know what it looks like, Mars, Jupiter, stripy. Earth's weather system is stripy, Jupiter's weather system is more visibly stripy. Saturn, stripy and has rings. I didn't bother getting measurements for the rings. And Uranus, just kind of misty, very faintly stripy. I haven't included Neptune, and there's a reason for that, which becomes really obvious if I type Neptune in up here. Very helpful of them to actually use the same format for all of these. You'll need to get to one of these. You can just type in the planet name to change it. It's a very pretty blue planet. It's a nice spot system, stripes, very elegant. The reason I didn't include Neptune is these numbers here. Bloody big numbers those are. That's millions of kilometres away. I'm sorry, but I don't own a sports hall. I could have rented a sports hall for this. I decided to just do it on the table, and the table ain't big enough. For what, as I was saying, anyone can do. What we've got here is a lot of sheets of paper laid out. 6 sheets of A4, so 297mm each. And this is a scale drawing of the solar system, with the distances and the planets drawn to scale. See, the Sun is down here, and they have 2 numbers. The perihelion and aphelion. This is as close to the Sun as it gets, this is as far from the Sun as it gets. For Mercury, Venus, Earth, Mars, heck of a big gap, a lot of asteroids in it. Jupiter, And we've gone from rocky planets down here to a gas giant, which has to do with densities of materials and gravitational fields and so on. And then way out here, Saturn, which has one heck of a difference, heck of an elliptical orbit, you know? It gets this close, it gets this far away. So as viewed from the Sun, looking along it, Saturn's all the way out there, at the gap between the last two sheets, and Earth is that close. Heck of a long way. As I said, this is a scale drawing of the solar system and the planets within it, including the Sun. Some of you may be looking at this and thinking I haven't drawn the planets. Yeah, the thing is, my zoom doesn't go in far enough for you to see them. This is the Sun to scale with those distances. That is a 1.2 millimeter dot, because that's how big the Sun is to scale on this scale where Saturn is all the way out there. Sun to Earth distance, 1.2 millimeter dot just there is the Sun. The Earth's radius at the equator, 6.4 microns, so its diameter would be like 6378 point something thousand kilometers really, but on this scale, because this is a 1 in 10 to the 12 scale drawing, its diameter would be about 12.8 microns, which is, it's kind of the diameter of a muscle cell, I think. It's too damn big to be a bacterium. There are amoebae bigger than that, and liver cells get bigger than that. Venus is about the same. Mercury is a lot smaller, would be 4.8 microns in diameter, which is just the large size for a bacterium. Mars, that's, what, 6.8 microns wide? Maybe a red blood cell? I mean, I could look that up. Erythrocyte diameter, 6.8 microns? So if you want a scale drawing of just the inner rocky planets, which just nicely fits on a sheet of A4 here, with the Sun, you've got a 1.2 millimeter Sun and a single red blood cell for Mars. Hey, red, it's even the right colour. And then Jupiter is a thing all the way out here, 71 micron radius. It's huge! Huge, I tell you. 0.14 millimeters in diameter. You can actually see it. It's that tiny little pencil. It's there somewhere. There's a pencil dot there somewhere, 1.14 millimeters in diameter, which is Jupiter, and then Saturn is out there, 0.12 millimeters in diameter. The rings are a bit wider, but the rings are very, very thin. They're like, dandruff would be overstating it. And the rest of it's out there. And on a different scale, that's 1 in 10 to the 12, this is 3 in 10 to the something else. I forget exactly now. Anyway, much different scale. Earth, instead of being 40,000 kilometers round, it's about 12 centimeters round. And yeah, that's the ISS orbit radius, just there. See, it's just visible. This is Antarctica, South America and Africa. Just from anyone who thinks it doesn't exist. Geostationary orbit, all the way out here. This is satellites that hang over little places like Ecuador, French Guiana, and Nyahururu in Africa, which are actually on the equator, which most of us aren't. Geostationary satellites that far out, and the Moon. To scale with this Earth, this thumb-sized Earth, it's yeah, this is where you see somebody holding up kind of a grapefruit-sized Earth, and he's holding up a golf ball-sized Earth next to it, and saying, "Hey, shouldn't you be able to see different features on the Moon from the North Pole and the South Pole?" Well, you can, but they're not very different. Why are they not very different? Because the Moon is actually kind of quite a long way away. It gets that far away. I've got markers for the closest and furthest distance, and I've just drawn it in between. Big chunk of mucky rock to scale with that Earth. And in theory, if I put the camera down here and look along there towards it, well, it's not a ball, so you can't really see it very clearly. but at that distance it is that wide. And if I then put the camera, we're going to see all kinds of junk when I do this, put the camera on Earth facing this way, just a piece of paper as a backdrop so you're staring at the right thing, and mark the width of Sol. It is, actually my hand started shaking, but it's, you know, there to there width, which ought to be the same width on the screen, explaining why the moon and the sun appear the same size in the sky despite being very different sizes. Just happen to be at distances in proportion to their sizes. Again, Sun, Mercury, Venus, Earth, Mars, shitload of empty space, Jupiter, shitload of empty space, Saturn, lots more empty space, Uranus, Neptune, and Pluto's just weird. It can't make up its mind how far away to be. It's at a different orbital angle. It's a pain in the butt. And Earth, shitload of empty space, the moon, that tiny little thing all the way over there. One more scale to get included in this while we're talking about what size things are. That's this one. This is a picture I made myself. Again, using information you can look up on like NASA, National Oceanic and NOAA anyway, National Oceanographic and Aeronautical Association or something like that. This is a very, very narrow slice of a cross section through the Earth, and you kind of need to zoom in a bloody long way to see it. No, that's a zoom. I want to look around. Oh, no, thank you. Right. Zoom in, up here, scroll, scroll, scroll. Drag the thing down. I may have zoomed in too far to make this easy. Is this even moving? Oh, there we go, it is moving. There's a label on it, mantle. Right. This starts way up at the top with ionosphere, mesosphere, stratosphere, troposphere, which is where the weather happens, and over here on the right, various mountains. Himalayas get that tall, Alps get that tall. These little white marks are the deepest gold mine somewhere in South Africa, and the deepest borehole, the Kola Peninsula borehole in Russia, where the Russians decided to just keep drilling and see what happens, because Russia. And we've also got the thickness of the continental crust in various places. Horizontally, this is not to scale. This is just little bits of the Earth's crust put side by side. Obviously, South Africa and Russia are not between the Alps and France. And just there for illustration purposes, this is oceanic crust, including mid-Atlantic rift. If I move the camera so far in that you can barely see, you've got mid-Atlantic ridges, mid-Atlantic rift, abyssal plain, continental shelf, and an actual ocean subduction zone trench. And all, zoomed out a bit, all the way down here is how deep earthquakes get. Zoom out again so that you can just see that earthquake marker up there. It is, oh, that's useful, isn't it? Pointing with a finger that fat. It is there. How deep earthquakes get. You're looking at mantle. And you're still looking at mantle. Scroll, and way down here, you're looking at outer core, inner core. And, well, it's not going to focus there, but I can zoom in. Inner core. Keep scrolling. And centre. I made it a very visible X, just so you can keep track of that when I'm zooming out. See, it's just here. That's centre still on the finger of that mouse, and I've just lost it. All the way up here is the crust. So when someone starts talking about, you know, curvature of the Earth and how far around it you can see, bear in mind this is Mount frickin' Everest right here. Mount Everest in K2 relative to sea level, right? So when you talk about how curved sea level is, bear in mind you are talking about a circle. Is this thing even going to zoom out far enough for me to see what I'm doing? Because it's not showing the inner core here. I should have opened this in different software. Yeah, you're talking about a circle with a... zoom the heck out. With a radius from all the way up there to all the way down here somewhere, on which Mount Everest is that tiny little wrinkle. So all those models you see with somebody with like a 1 in 40 scale Airfix Spitfire going around a 1 foot wide globe, they're not showing the scale of things properly. There are like 7 billion people on Earth thinking, no shit, Sherlock! If everybody watches this video. Somebody somewhere needed telling that. Scary, isn't it?